Welcome to Future in Focus. Today, we're diving into the world of humanoid robots and the unprecedented momentum driving their development. To start off, why are companies racing to build human-shaped machines at such an accelerated pace?
Great question. The surge is fueled by advancements in artificial intelligence and robotics hardware, as well as mounting labor shortages and new demands across industries. The goal is to create versatile tools that can work, adapt, and even interact with us in settings ranging from factories to disaster zones.
That versatility is key. It seems that human form is no longer just about appearance, it's about functional flexibility. But what roles are these robots expected to take on first as they roll off production lines?
Initial deployments focus on repetitive, physically demanding, or hazardous tasks. Think assembly lines, warehouse logistics, or search and rescue. These early applications serve as proving grounds for more complex, interactive roles in the near future.
Let's zoom in on Tesla's ambitious plan. Elon Musk aims to produce 50 humanoid robots by the end of 2025, expanding to 50 the following year. How does this production scale differ from previous robotics efforts?
Tesla's approach is unprecedented in both scale and integration. Unlike niche robotics firms, Tesla leverages its manufacturing expertise and vertically integrated supply chain to rapidly produce, test, and iterate on its robots, almost like building cars, but for intelligent machines.
That production mindset could be a game changer. Do you think this scale will push costs down and make robots more accessible to other industries?
Absolutely. As we've seen with other technologies, mass production typically drives down costs and accelerates adoption. This could put humanoid robots within reach for sectors like logistics, healthcare, and even private households, democratizing access to advanced automation.
Now, at events like We Robot, we've seen robots mixing drinks and dancing, often with some backstage assistance. How close are we to seeing these humanoids perform such tasks autonomously in real-world environments?
While demo performances are still somewhat staged, the underlying technologies are maturing rapidly. The leap from controlled demos to unsupervised real-world operation hinges on improvements in AI perception, dexterity, and environmental understanding areas where the latest models are making headway.
So, while we're not quite there yet, these demos signal what's possible as the tech matures. Can you give an example of a real-world application that's either imminent or already happening?
Certainly, robots are now being trialed in disaster response, entering hazardous sites where it's unsafe for humans. They're also starting to assist in warehouse logistics, moving heavy items efficiently alongside human workers, marking a significant step toward practical deployment.
The Tesla Gen 3 bot is quite impressive, standing 5'8", weighing about 125 pounds and featuring 28 actuators for human-like movement. Let's talk about the hands, which have up to 22 degrees of dexterity. How important is this for real-world utility?
Hand dexterity is critical. Humans rely on fine motor skills for countless tasks, from assembling electronics to folding laundry. The Tesla bot's near-human dexterity means it can handle delicate items or complex tools, opening the door to a wider range of jobs previously off-limits to robots.
In other words, anything we do with our hands, these bots could soon replicate. How does that compare to prior robot designs?
Previous robots often struggled with nuanced grip and manipulation. Tesla's progress narrows the gap, allowing for more surgical precision and adaptability. This level of control is essential as robots transition from industrial to domestic and service-oriented environments.
Tesla's robots harness the company's self-driving AI, trained with data from millions of cars. How does this vertical integration set Tesla apart from its competitors?
Tesla's integration lets them rapidly iterate on both hardware and AI in-house. By leveraging their vast driving dataset, they can teach robots to perceive and navigate complex environment skills transferable from roads to factory floors, and eventually to homes or even Mars.
That synergy between divisions seems unique. Does it mean Tesla can adapt its robots faster to new roles or unexpected challenges?
Exactly. This end-to-end control allows Tesla to test, refine, and redeploy both software and hardware with minimal friction. It's a huge advantage when scaling robots for diverse, evolving applications.
Looking beyond Tesla, the global market for humanoid robots was valued at $10 billion in 2024 and is projected to reach $39 billion by 2032. What factors are driving this explosive growth across the sector?
The surge is powered by breakthroughs in AI, improved sensors, and falling hardware costs. Demand is rising not only in manufacturing, but also in logistics, healthcare, and even consumer markets. Startups and established players alike are responding with innovative, scalable solutions.
Given this competitive landscape, what are some standout companies besides Tesla making significant strides?
Norway's 1X is notable, deploying their Neo-Gamma robots into real homes. Figure AI, with its Helix system, and China's Unitree, aiming for mass-market affordability, are also reshaping expectations for humanoid robot capability and accessibility.
Let's delve into Figure AI's Helix system, a two-part brain running onboard. How does Helix enable robots to handle tasks they've never seen before?
Helix consists of a perception module, a vision language model with 7 billion parameters, and a motion module with 80 million parameters. The perception side interprets spoken instructions and visual cues, while the motion side translates this understanding into fluid, context-appropriate Action 7 without prior task-specific training.
That's remarkably flexible. Can you illustrate this with a real demonstration or scenario?
Sure. In one demo, Helix was asked to organize a refrigeratora novel task. Without step-by-step programming, the robot identified objects, interpreted the request, and organized them, showcasing real-time adaptation. It's a leap closer to general intelligence in robotics.
Figure AI embeds the Helix brain directly within the robot, running on internal GPUs. Why is this onboard or edge computing a significant advantage over cloud-based systems?
Onboard computing eliminates reliance on external servers or stable internet connections, reducing latency and improving reliability. It allows robots to make split-second decisions on site, essential for safety and real-world viability, especially in environments where connectivity is spotty or absent.
That autonomy could open doors to deployment in remote or critical settings. Does this approach signal a broader trend in robotics design?
Yes, we're seeing a shift towards self-contained intelligence. As AI models grow more efficient, it becomes feasible to embed them directly into hardware, empowering robots to operate independently and securely in more diverse contexts.
If Tesla is scaling hardware and Figure is championing autonomy, Nvidia is building the digital infrastructure with its Groot project. Can you explain how Groot functions as a generalist AI for robots?
Groot is designed as a foundational AI model, much like how Android serves smartphones. It processes sensor data, simulated experiences, and vast video libraries to train robots for a multitude of tasks. With two systems, reflex and reasoning, it enables robots to react instantly or strategize as needed.
That dual system approach is reminiscent of the human nervous system. What impact does making Groot open source have on the robotics industry?
Open sourcing Groot accelerates innovation by allowing developers worldwide to build on its foundation. It democratizes access to advanced AI for robotics, fostering a global ecosystem where improvements and new applications emerge rapidly.
Turning to physical capabilities, companies like Boston Dynamics and Unitree have focused on mastering human-like movement. Why is locomotion such a crucial challenge for humanoid robots?
Human movement is a marvel of balance, strength, and adaptability. Replicating this in robots walking, running, or manipulating objects requires precise control and advanced mechanics. Boston Dynamics Atlas, for example, can now perform backflips, which shows how far we've come in mimicking our own agility.
Beyond showmanship, what practical benefits do these advances in movement bring?
Enhanced mobility lets robots navigate complex, unstructured environments, from disaster zones to crowded warehouses. The more fluid and robust their movements, the broader the range of tasks they can perform, making them valuable coworkers and assistants in unpredictable settings.
Let's discuss real-world deployments. GXO is already using humanoid robots in warehouse operations, and healthcare is exploring robots for elder care. What are the main benefits and challenges in these sectors?
Robots offer tireless labor, consistency, and resistance to injury or illness, ideal for warehouses facing labor shortages. In healthcare, they relieve staff by handling routine tasks like fetching supplies or assisting with mobility. The key challenge remains ensuring safe, empathetic interaction and seamless human-machine collaboration.
In hazardous zones, robots can replace humans entirely. Are there examples where this is already happening?
Yes, robots are deployed in nuclear plants, fire sites, or chemical spills, performing inspections or interventions that would be too risky for people. These applications are expanding rapidly as AI and robotics become more robust.
We're seeing a shift from specialized robots to those with generalist AI models that can learn and adapt on the fly. How does this differ from traditional automation?
Traditional robots followed rigid programming, excelling only at narrow, repetitive tasks. Generalist AI enables robots to interpret language, perceive their surroundings, and adapt to new challenges, much like teaching a person a new chore with words and gestures rather than code.
Could you put this into perspective with a hypothetical scenario?
Imagine a robot entering a home it's never seen before, being asked to load a dishwasher. With generalist AI, it can analyze the space, interpret instructions, and figure out the steps, demonstrating an ability to generalize from prior experience, not just repeat what it's been programmed to do.
As these robots become more capable, the real question is not what jobs they'll take, but what roles we're willing to cede. How might this shift reshape the workforce and society at large?
We're likely to see humans move away from repetitive or dangerous tasks, focusing instead on roles requiring creativity, empathy, and complex judgment. This transition echoes past technological revolutions. Machines augmented physical labor. Now they may augment cognitive or routine service work.
That's an optimistic take. But what ethical considerations should guide this transition?
It's vital to ensure that automation serves human well-being, supports fair employment transitions, and avoids reinforcing biases or inequities. Ongoing dialogue among technologists, policymakers, and the public is essential as we redefine what it means to work alongside intelligent machines.